A sub 0 is 2, and in general, A sub n is obtained by taking A sub n minus 1, the previous term, multiplying it by 3 and adding 2. So look at the roster of values we have. We have an n of 0, 1, 2, and 3. We know that A sub 0 is 2, which means A sub 1, since it's the next term after A sub 0, is going to be 3 times A sub 0. 3 times 2 plus 2, well, that's 6 plus 2 is 8. And notice, next to the 1 is an 8. So we sort of have ordered pairs here, which means that this is a function. If I give you 1 for this function, you get out 8. A sub 2 will be 3 times A sub 1 plus 2. 3 times 8 plus 2 is 26. And A sub 3 will be 3 times A sub 2 plus 2, or 3 times 26 plus 2 is 80. And you can see that the values will start getting fairly big very quickly and will never get small, because we're going to triple the number and add 2. Triple that number and add 2. Okay, so basically what we can see right now is we seem to be given a number and a rule. And the domain of our function, which is in the n column, or in this case was 0, 1, 2, 3, and it can continue going on. Those are called the whole numbers. 0, 1, 2, 3, 4, 5, so on and so forth. All the positive integers and 0. Also, we could have a recursive function where the domain started with 1. 1, 2, 3, 4, 5, 6. Those are called the counting numbers. And generally, the domain of a recursive function is either the counting numbers or the whole numbers. Let's look at the next visual. The next visual shows us another situation. We're given A sub 0 is negative 4, and that A sub n is equal to A sub n minus 1, the previous term, plus 3. And we have a roster. We've chosen n for 0, 1, 2, 3. We could show, of course, n's 4, 5, 6 on, and as long as you like to go. We're just looking at these 4 values of n. We know that A sub 0 is negative 4, so we've written 0, negative 4. That is an ordered pair. A sub 1 is going to be A sub 0 plus 3. Well, negative 4 plus 3 is negative 1. A sub 2 is going to be A sub 1 plus 3, which is negative 1 plus 3 is 2. And A sub 3 is going to be A sub 2 plus 3. 2 plus 3 is 5. You also can see that this particular function will continue increasing, because we'll continue adding 3 to each term. It will not increase as rapidly as the first function we looked at. We were actually tripling the number and adding 2. Here we're just adding 3 each time. Both of these will lead us to important kinds of results later on in this lesson. But I think we're at the point we can talk about what a recursive function is. What we've seen with recursive functions is that first we were given one value, one A sub n. In both our problems it was given A sub 0. We could have given any term, but A sub 0 or A sub 1, if that's the first term, is a good way to start. And then we were given a rule that if you know the previous term, you can find the next term. We then took the point we knew, or the term we knew, you might say. I say point because an ordered pair is always a point, as we'll see. We graph a couple of these recursive functions shortly. We took the point we knew, and we used the rule to get the next point. Or we took the term we knew, and we used the rule to get the next term, the next A sub n. So let's look at the next visual, which shows us, again, you heard it, now you just see it. A recursive function is a function in which one term is given. And the rule for finding A sub n, when you know A sub n minus 1, is also given. That is, finding the next term given the previous term. And you always do the same thing. You start with the term you know, you apply the rule to get the next term, you apply the rule to that term to get the next term, so on and so forth. You can actually go backwards. For example, if you were given A sub 4, you could apply the rule backwards. Subtract if you had to add, divide if you had to multiply, and get, if you had A sub 4, you could then get A sub 3 and use A sub 3 to get A sub 2. We will not talk about A sub negative 1. because all of the subs, the numbers we use for a sub 1, a sub 2, will either be counting numbers or 0. That is whole numbers or counting numbers. Okay, let's take a look at the next visual. The next visual shows us another recursive function. How do we know that it's a recursive function? First of all, they give us one term. Secondly, we have a rule. Given a sub n minus 1, here's how we find a sub n. In this case, a sub 0 is negative 4. And to find the next term, take the previous term and add 3. In fact, this is the same recursive function we just looked at previously. But now we have our roster, and we've also plotted points. Notice, if you look real carefully on what's the a sub n axis, which you could call the y-axis, I guess, at 0, negative 4, if you look real carefully on the screen, you can see there is a point there. And we've plotted all 4 of the points, 0, negative 4, 1, 1, 2, 2, and 3, 5. And I think I said 1, 1, and I think 1, negative 1. Let's go back again and talk about those points. 0, negative 4, 1, negative 1, 2, 2, and 3, 5. If you look at the graph, and we have the n-axis, which is kind of like the x-axis, because n is the domain axis, and the a sub n, which is the range axis. We've plotted those 4 points. If you look at them, what do you see? I think you say you see a line. Those 4 points appear to line up, and indeed they do. But we'll never draw a line here because, remember, our domain is only those whole numbers. We can't have a sub a half or a sub 0.6. So we'll have a set of points that line up and would appear to represent a line, but they're really just a set of points, a set of ordered pairs. Notice, if you go back in the visual to the roster, if I said to you, what do you add to the first a sub n, that is a sub 0, to get to a sub 1? You add 3. And you add 3 to that to get the next one, and add 3 to get the next one. In other words, we have what's called a common difference. And a common difference is very, very important. Let's go to the board and talk about this function and the common difference and how we can get another form of this function without using recursive form to get the same results. Let me go ahead and get my chalk, go here to the board, and what we had, the first point was 0, negative 4. And now I've written the ordered pair in parentheses as it was a point, because when we plotted that point. The second point was 1, negative 1. We are given 2 points. We are given 2 points that appear to lie in a straight line. Does that sound familiar to you? Indeed, way back in the early part of this series, we looked at finding the equation of a line given 2 points. But in the first step, you remember there, was finding the slope. And slope, you should recall, is how much y changes when x increases by 1. In a recursive function, n is always increasing by 1. So we might say, for a recursive function, the slope is how much a sub n changes as n increases by 1. But that's the common difference. In fact, if you have a common difference, you have a linear function, and that common difference is the slope. The common difference here was 3. So I'm going to write m equals 3. Now, if you want to go back and do negative 1 minus negative 4 over 1 minus 0, that's fine. You're going to get a slope of 3. The y-intercept is really easy to get because here it is. If we start with an n of 0, a sub n is the y-intercept, 0, negative 4. So we can simply write this equation, not y as a function of x, because that would indicate that any number is possible for x. We're going to use it as a function of n, because n indicates we're stuck with the whole numbers or the counting numbers. In this particular case, a sub n equals 3n, the slope times n, and then the y-intercept is negative 4. So this, you might say, is sort of a point approximation for the line y equals 3x minus 4. On the line, we have an infinite number of points between any two of the points here. That is, we could have an x of a half or 2/3 or the square root of 7. Here, the only values of n are 0, 1, 2, 3, 4, 5, because that is how we restrict the domain of a recursive function. And of course, the points we saw before would be points on the line y equals 3x minus 4. We could also check, as when we checked before we only had 2 points. When we were doing given 2 points, find the equation of the line through those 2 points. Now we have many points, right? We had 4 points, which is more than 2. Let's check using the next ordered pair, which was 2, 2. Let's see, does 2 equal 3 times 2 minus 4? Does 2 equal 6 minus 4? Yes, it does. The next point was 3, 5. A sub n was 5 when n was 3. So let's see, that's 3 times 3 minus 4. Is 5 equal to 9 minus 4? Yes, it is. In other words, you could check this out in all the values you have. And in fact, when you're given a recursive function, you can create as many values as you like, because once you have one term, you have the rule to get the next term. Okay? Let's go ahead and look at the next visual. The next visual gives us another recursive function. We have the value of a0 is 2. And we have the a sub n is equal to a sub n minus 1, the previous term, plus 2 times n plus 1. Okay? And if you look on the side there, we have a roster, n is 0, 1, 2, 3, 4, 5, and we have the values. How did we get those values? Well, we were given a sub 0 is 2. To find a sub 1, take the previous